Okay. Okay. So the question, the basic question, the starting question is, who is the cleverest between a human and a computer when we are interested by playing chess? And we got the answer some more than 20 years ago now, where Deep Blue won on Garry Kasparov, and then there was no more competition between computer and human, as computer are sure to win when in front of human. Um, Now we can ask the same question: who is the cleverest? When the challenge is to playing with chess, which means to move the pieces on the chessboard. And there the answer is completely different. As a 6 years old child is able to move the pieces on the chessboard, whatever the condition of light, the size, the shape of the pieces. He, he can do that very easily, even if you put the chessboard, for instance, in a swimming pool, and well, and absolutely no robot is able to do that at the present time. Well, it's possible to design a specialized robot to move a given shape of pieces on a given size of chessboard with a given light, but a robot which is able to do that on any kind of chessboard in any kind of environment, it is just not existing at the time being. So what is the difference between these two problems? When it comes to play chess, the computer is winning over the most clever guys uh, in the world. And when it comes to playing with chess, a 6 years old boy is able to win against any robot and any computer. There is a big difference between these two kinds of problem, which is completeness. When to play chess, all the information you need is very limited. So you need to know that the chessboard has 64 cases. You need to know the existence of the different pieces, the way they can be moved on the chessboard, the place where they are, and few 3 or 4 specific rules. And that's it. This is all the information you need to play chess. It's very limited, and the main difficulty comes from the combinatory aspect of the game. And our computer, present computer, founded on logic, have been made and are very performant to solve this kind of problem with complete knowledge and with a lot of combinatory things to explore. When it comes to playing with chess, the situation is completely different, as there is no limit to the information you may need um, to solve the problem. You need information about the propagation of light to be able to recognize the pieces on the chessboard. You need information about a lot of information about physics to know the inertia of your own body, to know the hardness of the pieces, to know, well, there is limitless information, and our computer, present computer, and logic, which is the foundation of our present computer, is not made to work with this kind of incomplete knowledge. So here is a picture of the competition between Kasparov and Deep Blue. So you have Kasparov here, you have Deep Blue here, and you have a guy here, nobody knows its name, but his position was to solve the problem of moving the pieces on the chessboard. Okay? So that illustrates different kind of intelligence, because Deep Blue is cleverer than Kasparov to play chess. This guy is cleverer than Deep Blue to play with chess, and Kasparov is certainly cleverer than this guy to play chess. So we have different kind of intelligence, and we will see along this 3 hours different examples of this different kind of intelligence, and the different problems that they're supposed to solve, to be solved. Well, 2 more slides on that. Where did the evolution lead computers? Well, the ancestor of computer were this, and the problem is just to solve very basic arithmetic question, to know how to do addition and multiplication. And in fact, they did not really change from that. They are still made to solve arithmetic problem and logical problem, and they have not been at all conceived at the beginning to solve physical and control problem in the physical world. For us, the evolution was very different, okay? The basic problem we had to solve, maybe not now anymore, well, but really the basic problem we had to solve was this kind of problem, where it's essentially a sensory motor problem to fight and to find to feed, and so this is a sensory motor problem and based really on incomplete information. Well, so my claim is that living beings like us have to solve incomplete problem. And I will talk a little bit later on of a much more simpler living being. Here you have, I'm pleased to introduce you to Chlamydomonas, which is a very small unicellular algae. And you will see that it's a fascinating being. And this algae has also to solve incomplete problem, and its basic question is how to use incomplete and uncertain information model of the environment. And you will see that it's a very basic model of the environment, but it has a model of the environment, and to perceive, to infer, because it's even this unicellular being is able to do some kind of simple reasoning to decide and to act efficiently enough to survive, which is the real question. So we will talk of different question. Why is probability better than logic to solve incomplete problems? I will give some example in robotics, how to learn reactive behaviors, how to take time into account, how to build more complex model. Maybe we'll talk a little bit about can we human do probabilistic inference, and there is different kind of answer to this question. How can living system perform probabilistic inference? And maybe if we have time, I will give you some small hints about my present subject, which is how can we build probabilistic machines? Well, anyway, this course is supposed to be an introduction to Bayesian modeling, so I hope I will give you some well, I will raise in you the envy to go further, but it is just an introduction. So why is probability better than logic for incomplete problems? The basic schemata is the following, is that we have incompleteness. So we have to solve problems where not all the information is present. In fact, usually we start from a model of the environment, which is the preliminary knowledge coming from, when it's us, we are reasoning, coming from us, from our brain. And we combine this preliminary knowledge with some experimental data. We combine that by learning, and we build some probabilistic representation from this combination of preliminary knowledge and experimental data. So in this process, which is very interesting, is that incompleteness. So of course, the preliminary knowledge is incomplete. There are some missing information. There are some missing variables, what the physicists call hidden variables. And the effect of this missing information is that the result of the learning may only be probability distribution. So in this process of learning, we transform incompleteness into uncertainty. And you will see several examples of that. Then, after this process, you have a mathematical representation of your problem with the probability distribution. And you can make some inference to solve problem and to reach a decision. So you can do Bayesian inference, and Bayesian inference is defined with two simple rules. Logical inference require only a single rule. Here we need two simple rules. And you will see how these simple rules can be used to do very complex reasoning to reach a decision.
Excuse me.
Yes?
I'm just wondering, why is the first step called Bayesian learning and the second called Bayesian inference? So like, what is the difference between them? And why is the first not also inference?
You mean, what is the difference between the first step and the second step? That's it?
Yeah, and also in terms of the definitions, so Bayesian learning versus Bayesian inference, technically what are they meaning?
Well, Bayesian learning is really consisting of, you start from a probabilistic model where a lot of parameters are not yet specified. Okay, so that's what I call probably preliminary knowledge. And then you get some data and you combine both of them to build probabilistic representation. Okay, so that's
Okay.
really learning. And then you have your probabilistic representation and you combine them to do reasoning to make a decision. So there is no more learning here, no more acquisition of more knowledge coming from data or from experiment. You just reason to make a decision.
So in the first step, you don't use Bayes' rule, for example.
Sorry?
In the first step, you don't use Bayes' rule, for example.
Well, that's a very good question.
Okay.
That's a very good question because, in fact, as we consider probability as an extension of logic and a very basic and powerful mathematical tool, there is a way to express Bayesian learning as a special kind of inference, okay? In a different space where the parameters that are learned here are considered as variable of a larger model, and learning can be really seen as inference in this larger model, which is to find the best model in a space of models according to the best model, meaning the models that can best explain the observed data. Okay,
Yeah.
so this is a very, very good question, but well, I have a lot of things to explain before coming to such a deep question.
Okay. Thank you.
Okay.
Yes, thank you.
Coming to probability, there are two, from a philosophical point of view, there are two ways to consider probability: the objectivist and the subjectivist approach of probability. So the objectivist approach considers that probability is a model of the world. The subjectivist approach considers that there is a subject, and probability is a model of the reasoning of this subject on the world. Okay? So you may consider that is a very philosophical and not very important point, but in fact it has a lot of consequences. In the objectivist approach of probability, it's, well, learning start from the data and is supposed to exploit the data without any knowledge coming from any other source. In the subjectivist approach, there is this subject. This subject has its own knowledge, what I call preliminary knowledge in the previous slide, and he has his own point of view on the problem. He is subjectivist in that sense because he has its point of view as a subject, and he will learn and interpret all the data he sees from this particular point of view.
I had a question on objective versus subjectivist.
Sorry, can you?
I had a
Well, just a second, because can you speak a little bit higher, because I have a hard time to hear you. Yes?
It's better.
Yeah.
Okay. I had a question on objectivism. Is it in any way linked to libertarian objectivism, or is it just its own type of objectivism?
Well, I'm not sure I want to answer this question now because it's quite a difficult question, and it will take maybe too much time. Maybe at the end we'll come back on this question if you don't mind.
Thank you, Henry.
Okay. So as you maybe guessed, I will defend a subjectivist approach of probability, and for me, probabilistic inference or learning theory consider as a model of reasoning. So this is the key point, as a model of reasoning, is an alternative and an extension of logic to explain and understand perception, inference, decision, learning, and action. So in the history of probability, the debate between subjectivist and objectivist has been present for the past 4 centuries, even if it was not called like this at all time. So, for instance, Jacob Bernoulli in 1713. So it's really at the very beginning of probability. Said, uncertainty is not in things, but in our head. Uncertainty is a lack of knowledge. A very subjectivist point of view. Laplace, 1 century later, is really the one of the father of probability. Said, la théorie des probabilités n'est rien d'autre que le sens commun fait calcul. Okay, I will maybe not go in all the instances here. There is a citation from Maxwell, a citation from Henri Poincaré in La science et l'hypothèse. I recommend you to read this book. It's really a very fascinating book concerning the modelization and the reasoning about the world. And our guru, which is James, an American physicist that unfortunately died 10 or 15 years ago. And I recommend you also to read his book, Probability Theory, The Logic of Science, about how to use probability to do reasoning. It's at Cambridge University Press. So, okay, I said that you need 2 rules. So what rules? Well, the first one is the normalization rule that says that if you have a variable A and the probability of this variable A, the sum on all cases of A, of the probability of A, is equal to 1, the normalization rule. So in this course, I will restrict all what I present to probability on discrete variables. So this is a choice because everything is much simpler when you come to a discrete variable. Because when you have to do probability with continuous variables, you need to introduce measure theory, which is some very elaborate mathematical tool. And the second reason is that as a computer scientist, I am convinced that present computer are just enabled to deal with continuous variable. So of course, we use them to solve a continuous problem, but there is always a discretization of this continuous variable, and this discretization is always a very dangerous process, and you have to never forget that there is this discretization, and you should always be very careful when using computer of the bias and errors that this eventually hidden discretization introduce. The second rule is very often presented this way as a Bayes rule, which says that the probability of A knowing B is equal to the probability of B knowing A times the probability of A and divided by the probability of B. In fact, I think it's a little bit better to present it as the product rule, which says that the probability of A and B is equal to the probability of A multiplied by the probability of B knowing A, and it's also equal to the probability of B multiplied by the probability of A knowing B. Okay? Of course, these two are completely equivalent. And this is really the two only rules that you need and that you have to combine in a lot of different ways to be able to do all the computations that are required by probability reasoning and probability knowing. So why is probability better than logic? Why is it more powerful? Well, I will talk of that during all the presentation, but I would like to give you a very simple example based on what is called the syllogisms. I hope my pronunciation is in English is correct for this word, which is really at the foundation of logic. And you have two of them, the modus ponens, which says that if A is true and A imply B is true, then you can derive that B is true. Okay, so let's take an example where you have A, which is a logical proposition that says that a number X is divided by 9. And B, the proposition that says that X is divided by maybe divided by 3. So if you know that X is divisible by 9, and of course you know that if X is divisible by 9, it is divisible by 3, then you can derive from these two knowledge that X is divisible by 3. In probability, this can be summarized as the probability of the proposition B, X is divisible by 3, knowing the proposition A, X is divisible by 9, is equal to 1. The second syllogism is the modus tollens, which says that if you know that B is false, and you know the implication, then you can derive that A is false, which is equivalent to say that the probability of non-A knowing non-B is equal to 1. The probability that X is divisible by 9 knowing that X is, that X is not divisible by 9 knowing that X is not divisible by 3 is equal to 1. Okay? But then logic has nothing to say when you know that B, X is divisible by 3, and you know the implication. Logic has just nothing to say about that, which is quite different from our own intuition, because we are convinced that if we know that x is divisible by 3, then there is a higher probability that x is divisible by 9 than if we don't know that x is divisible by 3. So in probability, we know that the probability of A knowing B, so that x is divisible by 9 knowing that x is divisible by 3, is greater than the probability that x is divisible by 9 knowing nothing else. And the rules of probability, Bayes rules, allow us to derive this. Okay? So in this example, very, very basic example, one of the most simple example you can imagine, you see that probability can do more than logic. And the same thing is also true for in the other way around. Okay, so in fact, a lot of people work on how to use this most power of probability in sensory motor systems to model them. For instance, here I present a schemata of the usual action, environment, sensation, perception loop, which here Bulthoff and Ernst propose to model with probability. So in our group, we introduce a way to build a probabilistic model for sensory motor systems and for robotics, which is called Bayesian-Programming. So Bayesian program is made of two parts: the description, which is a model of the phenomena, and the question, which is a way to ask and solve problem using this model. Description itself is made of two parts: the specification, which are the preliminary knowledge coming from the modeler, the programmer, and identification, which is the learning part. And the specification itself is made of three parts: the choice of the variables that describe the problem you have to solve and the model you want to build. So let's take an example. For instance, let's say that we have a variable s for the state at different point in time, so from time s0 to time t, and that you have an observation variable from time 0 to time t. So you have all this set of variables. Then you are interested in the probability distribution on all these variables that summarize all the knowledge you have about your problem. But of course, this probability distribution is very difficult to manipulate because it's really huge, as you have a big number of variables, each of them with a big number eventually of possible values. So you propose a decomposition. You rewrite this joint distribution as a product of sampler one. So here, for instance, but we will come back on that at several times. As it's a temporal model, we have the probability of ST knowing ST minus 1, which is a dynamic model of the phenomenon, saying that how the phenomenon evolved from a given state to the next one. And you have an observation model that says, if I am in a given state at time t, what are the observations that I can do in the environment at this same time? Finally, the third step of the modelization is that you have to give some parametrical forms to this elementary probabilistic distribution. And for instance, here, if you give to this elementary probability distribution the parametrical form of Gaussian law with some specific constraint on the mean and sigma, then what you obtain here is a Kalman filter, which is one of the most used and one of the oldest used probabilistic model. It became very famous as it was largely used in the Apollo mission to send a man on the moon some more than 50 years ago. Then you have some parameters, and they can be learned from instances, and we'll see examples of that. So that's the identification and learning part. And after that, to this description, you can ask different questions. So for example, you can ask the question, what is the probability to be in the state S, a given state at time t, knowing all the observation from time 0 to time t? We build an inference engine, so we can rewrite this different element in computer language, and then we have an inference engine that is able to do all the required computation automatically. Oops. Sorry. Oh. Okay. So I have 3 recess in when I pass from one subject to the next one, which are small experiences. So I don't know how this one will work when not presented in when you are physically present, but we will try. So it's a small perceiving experience. You have 2 teams, the white and the black. Each team has its own basketball, and the question is to count the number of passes between the white. Okay. So you have to be a little bit concentrated because it's not a very easy task. I will start. Okay. So it's not very easy to get your answers about the number of paces, but this is not the real question. The real question is who saw the gorilla? Okay, so I will try to come back to the movie. And now you don't count. And you will see that at some point, now there is a gorilla coming into the scene. And don't be afraid if you didn't see the gorilla at the first try. In fact, about 80% of the people don't see the gorilla. And this is to demonstrate that perception does not consist to be a passive spectator of the world. You always perceive with some goal, some action that you want to perform in the world. And in fact, this is an inconvenience because you miss a lot of things, but this is the basic tools you have to filtrate the enormous quantity of information that arrives from your environment. And this is really one of the basic problem of perception, how to select the pertinent information. And having a specific goal is really the main tool to do that. Okay, so I will start now the first, the second chapters on the application in robotics. Maybe I propose to stop for 5 minutes. If you, well, I propose to stop for 5 minutes, so we'll come back at 10:23. Okay?
Okay, thank you.
Okay.
Okay.
Thank you.
Okay, so let's start again. And we will talk about application in robotics. So here you have some instances of different work that has been done using Bayesian-Programming in robotics along the year, either in different universities, in Paris, in Grenoble, in Switzerland, in Portugal, well, at different places. So with very different robots. And I will go a little bit deeper in the presentation of some of these examples. So let's start from a very simple experience, which is how to learn reactive behaviors. And we did that a long time ago with a very small robot made in Switzerland, which is called the Kepera robot. And so here you have a €1 coin. So you see the size of the robot. And it's an interesting small robot which you can drive as a military tank. So he has 2 wheels, one on the right, one on the left, and giving different speed to these 2 wheels. You can drive this robot as a tank. And it has also a small light sensor that you can see here. And there are also infrared light emitters. And so you can use them either to measure light or to have an estimation of distance, because you send a small infrared wave and you measure the quantity of light that is coming back. And of course, if there is an obstacle close, there is more light coming back than if there is no obstacle or an obstacle far away. You can pile different plugin onto this robot. For instance, here you have a small hand, and this is a piece of sugar. And here you have a small fan that may be used to blow in front of the robot. And you have also different way to put simple camera on the top of the robot. And we will try to teach this robot some simple behavior, like avoiding obstacle, following contours, pushing obstacles, going toward light, and so on. So let's describe the way to build a probabilistic model for pushing obstacles. So I applied the method I presented earlier. And the first step is specification, which is to choose the variables. So to choose the variables, here I have a view from the top of the Kepera robot. So you have here the infrared light sensors and emitters, 6 in the front, 2 in the back. And from the information coming from these sensors, you may build 2 variables, one which is the direction, which is a measure of the angle between the front of the robot and one of the most interesting obstacle around the robot. The value of this variable dir goes from -10, which means completely to the left, to +10, which means completely to the right, 0 meaning in front of the robot. The second sensory variable is the proximity, which is the inverse of the distance, where 0 means no obstacles, and 15 means there is an obstacle very close to the robot. So the variable prox can vary between 0 and 15 on 16 different values. So that's for the two sensory variables, and we will have one and only one motor variable, which is the rotation speed, then can vary between -10 to +10. -10 meaning turn the fastest you can to the right. +10 means turn the fastest you can to the right. So that was to the left for -10. And 0 meaning go straight ahead. So we have three variables, which are direction, proximity, and rotation speed. So now we are interested in the joint distribution on these three variables, and we can use Bayes' rule to write that the probability of G prox and V may be right using Bayes' rule as the probability on D times the probability on prox on P and V knowing D. Then applying Bayes' rule a second times, you can write that the probability of P and V knowing D may be written as the probability of P knowing D and the probability of V knowing P and D. So here what I wrote is an exact mathematical relation, and the joint probability distribution is completely and really and mathematically equal to this product. But now, as a modeler, I can do some hypotheses to simplify my model. And here, for instance, I can say, well, I don't think there is a correlation between the proximity of the object and the direction of the object. So I consider that the probability of P is independent from the probability of D. And as soon as I do that, the relation is not mathematically exact anymore, and I introduce some preliminary knowledge in my model. Okay, so here it's a very simple and basic model, but this is really the main tool that we have as a subject, as a modelizator, as a programmer, to introduce simplification in our model, our probabilistic model of phenomena. Okay, so now I have this relation, and I can specify the parametrical form. So I can say that I don't know anything about the probability of D and the probability of prox, so I consider they are uniform. And I consider that the probability of the rotation speed, knowing the position of the obstacles, so D and prox, should be Gaussians. So here I have a family of Gaussian, okay, because I have 21 possibility for deer, 16 possibility for prox. So I have 21 times 60 different Gaussians. And these Gaussian have their parameter, which are the mean and standard deviation. And with the specification, I don't fix the parameter, and I will try to learn the value of this parameter. So 21 means 21 standard deviation. sorry, 21 times 16 means 21 times 16 standard deviation by doing some experiment with the robot. And for this, I will use a joystick to drive the robot to do some specific behavior. And finally, after all this will be performed, I will use this model to ask questions to my robot. For instance, I will ask the robot to drive itself without any remote control by deciding what should be its rotation speed, knowing the sensory situation at a given point. So here, when
In the first
movie
experiment,
starts,
we'll show how we can teach the Kepra to push
can you hear
obstacles.
the sound?
The robot can be
Yes.
operated in 3 modes. In the first mode, we just joystick the robot in the environment. That's what we show here to give an example of the objective behavior. In the second mode, the robot is still joysticked, but at the same time, it's gonna learn the behavior we show. Finally, in the third mode, the joystick is not used anymore, and we ask the robot to play back what it just learned. We see that there was already some sort of pushing of obstacles, but we can teach further by showing some interesting situations. That's what we do here. We show the robot, by short sequences, some more interesting situations. We now put back the robot in restitution mode. It knows fairly well now how to push obstacles. However, at any time, we can try to perfect the behavior by showing again some more situations. For example, what has to be done if the obstacle is on the left? What has to be done if the obstacle is on the right? Finally, after about 25 seconds of learning, we finally put it back in restitution mode to check how well it pushes obstacles.
Okay, so you see that in just something like 30 seconds, it's possible to give a force very rapidly a first way for the robot to do piano mover behavior and pushing obstacles. In fact, it's a very simple behavior as it's reactive, and essentially what the robot has to learn is that when the obstacle is in front of him, so the direction is 0 and the proximity is 15, to push the obstacle, he has to go straight. So the probability distribution on the rotation speed is a peak, a Gaussian, with mean 0, saying you have to go straight. If the obstacle is on the left, direction -10, and proximity quite close, the behavior the robot has to do is to turn on the left to come back to the situation where the obstacle is in front of him. So the distribution on the rotation speed is a Gaussian with a mean, a negative mean, saying you have to turn on the left. And if the obstacle is not present or very far away, then the robot just does not know what to do, and he has a very flat probability distribution, saying that, well, all the rotation speed are equivalent. Okay, now we will try to do contour following behavior. So the variables are the same one. The decomposition is the same one. the parametrical form are exactly the same. And the only thing that will change is that we will drive the robot to do this different behavior, which is contour following. So the set of experiment to do the learning of the 21 times 16 means and 21 times 16 standard deviation will be different. And we hope that starting from the exact same preliminary knowledge, by changing the data, we will obtain something completely different. So here we drive the robot to do the contour following behavior. Okay, so we started from the exact same point than in the previous experiment, but we drive it to do something different. Okay. And after a simple, a single tour of the obstacle, then we can ask the robot to do by itself the contour following behavior. And we see that it learned it pretty well. And it also learned, as it's a reactive behavior, you can change the obstacle, the shape of the obstacle, and it will still work. So here it is following a different shape of obstacle with no special difficulty. Of course, it's also a very simple behavior, and the only thing that change is that the Gaussian are quite different. So here we are in the state where the obstacle is on the left and quite close. So that's the pushing Gaussian that was learned. And this is the following Gaussian that was learned, which says that if the obstacle is on the left, as I learn to follow the obstacle on the left, I should go straight. And this is the situation. Oops, sorry. When the obstacle is in the front and very close. So to push, I had to go straight, and to follow, I had to turn to the right to try to get back to the position where the obstacle is on my left, and I could follow it. So in his PhD work, Olivier Lebeltel did much more complicated so here we tried to do a night watchman task. So the robot has to patrol the environment and to do different tasks. Here we lighted a small fire. So the robot is detecting it. It tries to blow with the fan on to extinguish a fire. It does not succeed, so he tries again. Now he succeeds. It goes back to patrolling the environment. It stops at some point to detect movement, because it should not be any other movement than itself, as it is a night watchman task. And then at some point, it has to go back to his home. And it does that doing a light following behavior because there is a small light over its home. And it stops when it gets to its home. Okay, so what's interesting here is that the robot learned something like 10 different basic reactive behaviors. And then, thanks to probabilistic inference, you can combine these different probabilistic behavior to obtain this more complicated one. What's interesting also is that there is no geometrical model of the environment. So you can change the position of the walls, you can change the position of the homes, you can change the different obstacles, you can change the position of the fire. Everything will still work most of the time. Why I said most of the time is because we present that for the Fête de la Science in Grenoble a few years ago. And la Fête de la Science is in a square in Grenoble, and there is a pool in the middle of the square. And the stands where you present your experiences are around this pool. So this works very well from 10 in the morning to 10 at night. It was very robust, but between 5 and 5:15 p.m., it didn't work. Why? Because the sun was reflecting on the pool, and the light of the sun, the light of this reflection was perceived by the robot as a fire. And for these 15 minutes, the robot tried to blow on the reflection of the sun to try to extinguish it, and with no success. So it's robust, but of course, it has also some limitation.
Excuse me.
Yes?
Just a clarification question. If we go back to the slide with the probability curves.
Yes.
Yes, here.
Here?
With the curves, as you just showed.
With what, sorry?
With the graphs of the probability.
Okay. This one,
Yeah.
for instance?
Mm-hmm. So the idea is that the robot selects the rotation, which is the maximum of the probability distribution.
Oh, that's a good question also. A very good question, in fact. So you have two different strategies. I would say the optimal one, which is in fact quite stupid, and the suboptimal one, which is more interesting. So the optimal one consists for the robot to decide for the maximum of the probability distribution. It is optimal because it corresponds to the best choice that you can do. But it is stupid in the sense that there is always a compromise between exploration and exploitation. So choosing the best value consists in choosing exploitation, but you have no more exploration, okay? So if you are in an unknown or not well-known situation, you will persist in doing always the same behavior, and you will not try to do some alternative behavior. trying to do some alternative behavior consists in, instead of doing and deciding for the best value, in drawing at random with this probability distribution. So most of the time you will do that, but sometimes you will do, for instance, a decision to have a rotation speed of -2 or +3, and so on. And you do some exploration. And for instance, if you are in a situation like this, okay, and your robot want to go toward this goal, okay, you will, the probability distribution will, to go towards this goal, I should go straight, and you will be there and be blocked there, okay? If you have some draw at random for exploration, you will have some chance to, at some points, turn and get out of your blocked situation. Okay. So, in fact, for the Kepera and for the other experience, we always choose to draw at random according to the probability distribution. And this is more interesting because if you have a very picky situation like this one, okay, drawing at random and choosing the best value is nearly the same. But if you have much more uncertain probability distribution, then drawing at random is very different and give you this capability of exploration.
Yeah, I see.
Is
And
that the answer
it's
to your
clear.
question?
Yeah. And I also wondered about the discretization, because I'm imagining that you tell the robot to sample at a number of discrete time steps.
Sorry, I can't hear you. Can you speak up a little bit?
So I wondered about the discretization into the different time steps, because I'm assuming that you sample at discrete time steps from this distribution.
Yeah, for the Kepera robot, the time step was, I don't know, something like 1/10 of a second.
I see. Okay.
But it really depends. I mean, you know, with this small robot, everything is very easy. You will see experiences with cars in the next video, and then you need much more computing power, and you need to sample much faster. Or, well, it really depends on the application.
Yeah, I see. Thank you.
So here in another thesis, Cédric Pradalier, who is now a professor at Georgia Tech, use that to learn behavior to small cars. So here you have the car that has to follow the road, avoiding obstacles. So it avoids a first car. Then he will try to pass the second car. Here you have a completely unconscious student that dropped his keys in front of the car, and nobody was holding the panic button. So I was panicked myself. Okay. So it seems very different from the Kepera, but it's, in fact, it's not. It's just a bigger car, and you need with more elaborated sensors, and but the complexity of the task is not very different. Well, here you try to learn a trajectory, But in fact, so that was the learning phase. You don't learn really the trajectory, but you learn the behaviors according to these markers here. Okay. And the robot, in just one try, learn how to get back to his garage, also avoiding obstacles. Okay. Maybe just a remark about avoiding obstacles. It's well, it was difficult at the beginning to avoid obstacles, and then the students proposed to do some proscriptive programming instead of prescriptive programming. So just to explain that in a few words. For instance, I have this probability distribution that express where to go to the robot, the direction, and you have this probability prescriptive, so saying what to do when there is an obstacle in front of you, that says what to do when there is the obstacle in front of you. And combining these two probability distribution is difficult because, well, the good solution is somewhere here or somewhere here, but it's not very easy to find. Now there is a different approach where you have yet this prescriptive probability distribution saying where to go, but to avoid the obstacle, instead of saying what to do to avoid the obstacle, we said what should not do. So the probability distribution looks, for instance, like this, because the obstacle was here, okay? And so I should not go here in this direction. And, oops, sorry, I lost everything. Well, oh no. So combining the blue and the red distribution, now you have this solution and this solution, and this is a much more efficient way to combine the probability distribution. Okay, so that's few examples for the robotic part, but we did a lot of different things with arms and also in Switzerland they work on that to do and to learn maps in labs, and well, if you are interested, I can give you pointers on all these theses and papers. Okay, now I will try to give you some example of the importance of taking time into account. And this is called Bayesian filters, and it has a lot of applications. So let's get back again to the programming, Bayesian programming method. So the variables, I already present them. You have state variables between time 0 and time t, and observation variable between time 0 and time t. The joint distribution is really huge, okay? Because if the times, for instance, is from 0 to 100, then you have 200 variables. Each of these variables may have a lot of possible value, and the size of this space is the number of value for variables to the power of the number of variables. Okay, so for instance, if you have 10 possible value, which is very small for the state and observation variables, the size of the space is 10 to the power 200. Okay, so there is no way you can work directly with this joint distribution. So you have to make very important simplification by writing this joint distribution as a product of simpler one. Okay, and for this we'll do the same thing then for the Kepler. We can write using Bayes rule. We can write, so I will try to do that. So the probability of S0 to ST, O0 to OT is equal to the probability of the original state, S0, O0, the probability of S1 knowing S0, O0, the probability of O1 knowing S1, S0, O0, okay, and so on. The probability of ST knowing S0 to T minus 1, O0 to T minus 1. The probability of OT knowing S0 to T, O0 to T minus 1. Okay? And I will make some simplification. So I will say that, well, if I know S0 here, then I don't need O0 to predict S1. So I will do this simplification. Here, if I know S1, I think it's a sufficient information to know O1, and I don't need S0 and O0, and so on. Here, if I know ST minus 1, it's sufficient to predict ST, so I keep only ST minus 1. And here, if I know ST, it's sufficient to predict OT, and I can neglect everything else. So at the end, what we got is a dynamic model which says that knowing ST minus 1, it's a sufficient information to predict ST. Okay, so I made a huge simplification here. For instance, I neglect the state before T minus 1, so I make what is called a Markov model of order 1, because I only take into account the state just before and not the other ones. So that's a dynamic model. And here it's an observation model, which is the probability to have information on the observation at time t is sufficient to know the state at time t, and I can neglect everything else. So here at the end, I have a huge simplification, because now I have only to get back to the example. If the number of possible values for S is 10, I have a distribution with 10 possibility for S at t minus 1 and 10 possibility for S at t. So it's only 100 times 100. And here it's also 100 times 100. Okay. And this is not anymore to the power of t, but time t. Okay. So here it was 10 to the power 200. Here it's something like 100 for t times 10 to the power 2. Okay? So you see that the complexity of the two is completely different. The final step is that I have to choose a parametrical value for this. We saw already in the previous examples that for Kalman filters, it was a Gaussian choice, but you can make very different kind of parametrical choice here according to your problem. Then you have these parameters that are still free, and you can do some learning to identify the value of these parameters. And then you can ask different questions. The basic question is probability to be in a given state ST, knowing the observation from 0 time t. But you can make more different questions that, for instance, the probability of a given sequence, S0, S1, ST, knowing the observation of 0 to t, which is, for instance, to recognize a given trajectory. You can make a lot of different questions with different difficulties, of course, for the computation to solve them.
Excuse me.
Yes?
About the previous slide, the huge simplification that you use in the decomposition step, I guess that's what you call the conditional independence hypothesis.
Sorry?
Sorry,
I didn't hear the last word.
Yeah, so the simplification that you obtain, it's the you obtain it thanks to the conditional independence hypothesis, right?
Yeah, exactly.
Can you explain why we are justified in making such an assumption?
Well, it's not justified, okay? It's really your choice as a modelizator, as the subject of the subjectivist approach of probability. So you decide, because you have some knowledge of your problem, that you believe that this conditional independence makes sense. So it's really your own knowledge, your own choice to make this hypothesis. Well, of course, usually this hypothesis makes some physical sense if it's a physical problem, or well, if it's not a physical problem, if it's I don't know, an economic problem, it makes sense from your economic belief in the model you are building. So, for instance, the dynamic model make sense if you make the right choice for the state. I will give you an example just after that, several examples of that. The same for the observational model. You believe that a given state is sufficient to explain the observation you have, and you don't need the history of the whole process to explain the observation you are making. Is that
Okay.
an answer to your question, or?
Yeah, I think I understand better with examples.
Yeah. So before coming to the example, just a very important remark about this kind of model is that there is a possibility to do recursive computation. So here we have what is called the prediction. So maybe I should write it bigger. It's the probability of S time t knowing observation from 0 to t minus 1. Okay? It's called a prediction because it's t minus 1 here. So you have the observation, but the last one is missing, and you make a prediction on the state in which you will be. Okay? And the math proves that this is obtained at the sum and the state t minus 1 of the product of the dynamic model, probability of st knowing st minus 1, time the evaluation of st minus 1, knowing all the observation from 0 to t minus 1. Okay? This is called the evaluation. So the evaluation is here. So you have the probability of st knowing O0 to t, the probability to be in state t knowing all the observation. So you see the difference between here and here is that you have, oops, sorry, one more up. You have one more observation. Okay, here it's t, here it's t minus 1. And the math says that this is equal to the product of the observation model, probability of OT knowing ST, time the evaluation, the prediction distribution, the probability of ST knowing O0 to t minus 1. Okay, and here comes the recursion, because the prediction here appears here. Okay, and the evaluation here appears here for the next time step. So you have this recursion where you do the prediction. The prediction is used to do the evaluation. The evaluation is used to do the prediction at the next time step, which is used to do the evaluation at the next time step, and so on. So this is a very important feature, and it is used to sorry, it is used to do a lot of simplification in the computation. In fact, you use that kind of mechanism every day when you are using a GPS. So the GPS starts from a given state when you turn it on, where the state in GPS is the position on the Earth and the speed, the combination of the two. So when you turn it on, usually it has only a rough idea of the region in which you are and no idea of the speed. So you have this distribution on position and speed. Okay. Then you make a first prediction. So the probability, you evaluate the probability and the state at time 1, knowing the first observation. And in fact, at first you have a dispersion because you have no idea of your speed. Then you make a second observation and you can evaluate your position and speed according to these two observations, doing this product. And as you made a second observation, then the probability distribution is more precise than at the beginning. Then you make a prediction. So as you have a first evaluation of the speed, your points are moving in approximately all the same direction, knowing your first evaluation of the speed. Then you make a third observation. And you have a concentration of your point. A new prediction. A new evaluation. Okay, and after a while, you have a much better evaluation of both your position and speed. In fact, with GPS in a car, it's not very easy to see that because there is another constraint, which is the road, and the GPS knows the map and constrain your position to be on a road and not anywhere else. But if you use a GPS on a boat, for instance, you can very well see this process, because when you turn on the GPS, your position on the map can be false from 1 kilometer easily when you turn it on. And after 1 minute, your position is, the precision of your position is something like 5 meters, okay? So you have to turn on your GPS before being in the middle of the rocks. Okay, another example is a work made on Bayesian occupancy filters. In fact, there was several theses on this subject along the years, and also, as you will see, some industrial application. So the task here is to try to have the relative positions of obstacles in front of a car for ADAS. So ADAS means trying to helping the driver to drive safely. Sorry. Sorry, I drink a little bit because so let's start by supposing that we have here you have the grid, okay, in front of the car. So the grid is linked to the car. It's relative to the position of the car, and it is divided in small cases, a lot of them, 10,000 or something like this. And the task is to try to find which of the cases of this grid are occupied or not. And we will start with the single sensors. Here, for instance, let's say that it's a LiDAR that is able to detect that there is a possible obstacle at some point. So for instance, here you have a detection, and what you obtain, so here you have the grid, okay? And according to this detection, you may build a probability distribution of occupation of each cell of the grid. So at this point, you have a high probability of occupation as you add a detection there. Here you have a low probability of occupation as your sensor said that there was no detection. So it's in purple. Here you are out of the scope of the sensors. So you just have for each cell a probability of 1/2 to be occupied, because you don't know if there is something or not, because you have no detection there. And finally, you have this special area where you don't know also if it's occupied or not, because it's an occultated space as it's behind this object. And this object is hiding this space to your sensor. Okay, now you can do that with several targets. So you have the detection of these two, and here you have only the occulted space. Why? Because in fact, instead of having one single grid, you have a pile of different grids for each possible speed, relative speed of the object. So this object was moving in this direction, so it doesn't appear as a detection for this speed, but for another speed, for this one, okay? So it's a multi-dimension space. Now you can do that with 2 sensors and 3 objects, for instance. So here what you have, you have a very high detection for this, because it can be detected by both sensors. You have detection for these two, which is a bit lower because it's detected by only one sensor. And you have a very low probability of occupation here, because it's a space that is may be detected by both sensors, and both sensors says that they didn't detect anything. Okay. Now, for the time being, there was no time filter. So what's happening is that as soon as you are not in a zone where there is a possibility of detection, your target is disappearing instantly. Okay? This is quite bad. Let's take the example of a boy that is running behind his ball, and the ball is and the boy are disappearing behind a parked car, and you are coming with your own car. You will make the prediction that the ball and the boy will reappear in front of you, and you will brake. If you have no time filtering, when the boy is disappearing, it means that you think that the boy disappeared, and you will not brake. So you need some time filtering to keep the track of the boy. And with this time filtering, the target is not disappearing instantly, even when there is no more detection. Why? Because there is a time persistence. you see also a very interesting phenomena, which is the free space, where you are very convinced. Black means that you are nearly certain that there is no obstacles. And why are you so convinced? Why there is a so low probability is because both sensors said at time t, I made no detection, then there is nothing. At time t plus 1, they make the same observation, there is no detection. But I know already that at time t it was free, so now I'm more convinced that at time t plus 1 it's free, and so on and so on. And after a while, you are completely convinced that there is no obstacles in this black area. Okay? So this is a very important feature, and obviously our brain is using that a lot. For instance, you have to know that on your retina there is something that is called the blind spot, which is the start of the optical nerve. And the blind spot on your retina is quite big. It corresponds to the size of your hand when you have the arm. When you look at your hand at the end of your arm, so it's quite a big spot, and you have absolutely no perception of this blind spot in the middle of your optical fluid. Why? Because your eyes are in constant movement, doing saccades and doing even microsaccades when you are looking at a precise point. And obviously, there is some time filtering going on. I don't know if it's probabilistic, but it's the same kind of mechanism that help your brain to fill this blind spot with some information. And there are a lot of perceptual behavior where you need this kind of consideration, especially, for instance, feeling with your fingers, where you don't feel the totality of an object, but you are able to complete your feeling at some point by some assumption of continuity and some perceptions that you made just before for the other point.
And so,
Yes?
excuse me, this is performed by recursive computation again?
Sorry?
This is performed by recursive computation again?
I'm sorry. I really hear you very badly. Say it again, please.
Non, pardon, peut-être en français. Je demandais si c'était de nouveau de la computation récursive qui était utilisée ici.
Oui, absolument, oui. Je vais essayer de changer de casque parce que je vous entends très mal. Just a second. Allô, vous m'entendez?
Oui,
Oui.
très bien.
Allô, allô?
Oui. Vous entendez?
Allô?
Oui,
Oui,
alors-
on vous entend.
Oui.
Ouais, mais manifestement avec l'autre casque, vous m'entendez pas, donc je vais continuer avec celui-là. OK.
Monsieur, je
here-
crois qu'on vous entendait avec l'autre casque, hein.
c'est l'inverse, c'est vous qui nous entendiez pas. Parce qu'on
Ouais,
on
ouais,
répond.
non, mais j'ai
Ah oui.
repris mon ancien casque parce que vous m'entendez pas avec l'autre et là, je vous entends très mal avec celui-là, mais on va faire avec. Okay, so the same example with the boy, okay? Here you see that, well, even when the boy is disappearing behind the car in the occulted space, there is still a probability that this is occupied. And you keep in your mind, in your reasoning, that there is a possibility to have an obstacle in the occulted space, thanks to the time filtering. So the boy here is this mark. It disappears behind the car, but yet the car is braking. You can see the same thing seen from the car, so there is no boy, but yet you are braking because you know that it will reappear and that you should avoid it. Okay, this was applied in more, we have a company which is called ProBase that has been funded nearly 20 years ago, and now it's quite big. And here you have an application for ADAS made for a Japan company. You see that we drive on the left. And so there is a detection of cars here made by cameras, possible detection of cars. Okay, here you have the probability grid. And here you have an estimation of the position and speed of the car. And you see also that there are some false alarms, but due to the time filtering, it helps to suppress some false alarm. Not all, but most of them. And this system is used not for automatic driving, but for eventually signaling to the drivers that there are some dangerous possible behavior and that he should take care of them. Here you have the same kind of application, but you can do also the fusion from different sensors. So here you have two cameras, and they are the information from the two cameras are fusion in a single information on the location and speed of the target. Okay, how to build more complex models. So it's possible to really combine this behavior to obtain a much more complex one. And we will see here another example, which is a special kind of robotics. It considers the problem comes from a video game. Here, StarCraft. We work on different video games, but here it's StarCraft. So depending of the audience, I have to convince that video games are very interesting and a very clever activity. So StarCraft is a good example because it's a mix between strategic games like chess playing and piano. Okay? So you can see the speed of the fingers of the good players. That's where StarCraft is looking like piano. You have to know that the number of action per seconds for this very good player is around 300 to 400 action per second, which is exactly the same speed like a piano player playing a very allegro piece of music. Yeah, per minute, sorry, you're right. It's 400 action per minute, not per second, of course. But it's already a lot. And what's interesting also is that these very good players are training themselves to do sequence of action, exactly like a piano player is training to do some given sequence of finger movements on the keyboard of the piano. But then StarCraft has another dimension, which is to make tactic and strategic choice according to what he wants to do for the game, like in chess, but with much more combinatory than in chess. So, for instance, the combinatory of chess is 35 to the power 80. 35 is the number of movement at one time, and the number of time is 80 because an average chess game is made of 80 movements. In StarCraft, the number of possible movements is very high, and the duration of a game is very high also. So the combinatorial power is incredible. There is another difference between StarCraft and chess, is that, as I say, the playing chess is a complete problem. There is no partial information. There is no randomness. At the difference with poker, for instance, where there is a lot of partial information because you don't know the game of the other. And in StarCraft, you are in a mixed situation because you don't know the position of your opponent. You don't know exactly the position of your opponent on the board. You know only some information, eventually outdated, about the position of your opponent on the board. So you have a lot of partial information. Now in StarCraft, you can organize the decision in 3 levels: the micromanagement with a time constant of about 1 second, eventually a little bit less. The tactics with a time constant of around 30 seconds, and the strategy with the time constant of about 3 minutes. And there is vertical continuity because your strategic decision have some importance on your tactics, which have some importance on your action. And also some information is, of course, going back because your observation may influence your strategic decision. And you have also continuity in time, because when you make a given choice as a micro action or as a tactic, then you want it to keep it going for a while before changing and not changing too often. So this is the continuity in time. Okay, so Gabriel Sinev, in his PhD thesis, work on StarCraft. He is now at Facebook, working also on games at Facebook. And I will not go in the details, but you can read his papers or his thesis. and I will just give you some examples. So this is an example of microcontrol. So the red are the ones that are played by Gabriel's artificial intelligence. The blue are played by the game artificial intelligence, and the red are winning quite easily because essentially they make decision to withdraw, clever decision to withdraw when they are in bad condition. In fact, microcontrol is the place where the artificial intelligence is doing best, even facing humans, but it's a little cheated because, of course, the computer can make much more often decision to move than the human.
Sir, excuse me, can you
Played
repeat
right there by Stork.
the
Every
person's
unit does
name,
come, but it looks
the
like
name of,
Oops. Sorry?
can you repeat the name of this researcher, the researcher who does this work on StarCraft? I tried typing it on the internet, but I didn't get it right, I think.
It's written.
I think someone posted it in the chat. Sorry.
Yeah, that's correct. I think it's written somewhere, but okay, anyway.
played right there by Stork.
So
Every
this
unit
is the
does come, but it looks like
tactic
he's going to come in
decision
here with the
where,
Shuttle Reaver once again.
there
Will he
is,
get the shot off? There's a
a
pylon in the way,
decision to make
and when
a
there's more
drop.
structures in the way, it's less likely that the
A drop
Scarab
is a
will hit,
special,
and there is another dud.
action
So
in,
really
tactical
lucky here
action in StarCraft.
for...
And here is a schemata of a more strategic decision. Because at StarCraft, there are some openings, like in chess, and it's quite important to try to guess what is your opponent's opening. So here you have in times, at first, the AI thinks that the opening is a two-factory opening, and the probability of this opening compared to other one change in time. And at some points here, there is an observation that is made on the board that I don't know which observation is made, but the probability of the two-factory opening is dropping when the probability of the drop opening is winning and goes nearly to 1. And of course, this strategic information is important to decide of what could be your own game. Okay. This is the second recess. So you have to try to answer this question very quickly. It's a very easy question. De quelle couleur est la neige? Que boit une vache? And I think that the first answer that came to your mind considering the second question was milk, which is obviously wrong. A cow is not drinking milk, it's drinking water. But the first question put you in a mind the color white. Then a cow is calling also white for milk, and milk is also coherent with drinking. And that's why usually milk is the first answer that came to your mind, even if you change rapidly. This is to demonstrate that it's very probable that you are not making purely logic reasoning. Your mental process is more a kind of a dynamical process. and it can be influences by very different information, even not very relevant to the real question. I don't say it's probabilistic, but it's not purely logic. I propose one more 5-minute breaks, if you don't mind, because in fact it's quite tiring to speak without any feedback of anyone. So let's say that we will start in 5 minutes at 11:32.
Thank you.
Okay.
Thanks.
Okay, let's start again. So the question now is, can we, as humans, do probabilistic inference? So the first question is, can you consciously solve probabilistic problem? And I mean, by consciously, it means using probabilistic rules. And the answer is rather no, or most people have a lot of difficulty to use probabilistic rules, which may seem counterintuitive. For instance, here you have the Monty-Hall problem. I will not explain it because it would take too much time. But for instance, the description on Wikipedia of the Monty-Hall problem is very well known and very convincing. But the result of the Monty-Hall is really surprising, and most of the people would make the wrong decision trying to use probability rules to solve this kind of problems. But there is a different question, which is your brain and nervous system using probabilistic reasoning unconsciously to make decisions? And for instance, there is this very surprising experiences made by Xu and Garcia, which shows that apparently a baby, I think it's yes, it's a 8 months old baby, use a kind of probabilistic reasoning when observing the environment. And the environment here is made of a box where there is red and white balls, and someone is drawing balls from the box, and it's drawing a lot of red balls and few white balls, and then you open the box and you show the baby that in the box there is much more white than red balls, and this is of course an unexpected result, and the baby is surprised. You can measure the surprise of the baby by different means, using, for instance, the interest he has to observe the box, or the way, the number of reaction of such or such kind. And when you have the same draw, but you open the box with more red balls than white balls, the baby is not surprised. So to explain these two different behavior of the baby, you have to suppose that he is making some kind of statistical probabilistic reasoning about the quantity of white and red balls in the box, which is quite surprising for an 8 months old child. In fact, there were a lot of people that did a lot of experiment in, especially in psychophysics, and trying to use probability models to explain these experiences. Probability are very good to explain illusions. For instance, here, I don't know if you understand this image, because it's quite strange at first view. In fact, the explanation is that what you are looking at is a mask which is turning always in the same direction, and at some point you observe the exterior face of the mask, and at some other point, so here is the exterior face of the mask, and starting now, we observe the interior of the mask, okay? And it's very difficult because you have very strong prior. You have the prior that the face is concave. You have a prior that the light should not change from one side to another. You have the prior that this is a rigid object. So it's very difficult to have a part of this object turning in one direction, the other part turning in the other direction. And this prior, which are very strong prior about the physics of this world, are not in coherence with the image you see until you understand that you see a mask, so you don't see always the same part of the mask. So probability are very good to explain illusion because the essence of illusion is the following, is that perception is an ill-posed problem. So when you have a perception, usually you have thousands, even unlimited interpretation of this perception. Okay, one of the most simple case is the Necker cube. Okay. And when you look at this cube, in fact, well, I should have here. Voilà. When you look at this cube, of course, it's not very well drawn, but you have two possible perceptions from your visual data. Is one with this corner in front, and one with this corner in front. If you draw an ice cube on a piece of paper, you will be able to switch from one perception to another perception. But in fact, there are a lot of other possible interpretation because it could very well not be a cube, but a more complicated shape that you see as a cube given your point of view. So you have endless possible interpretation of this image on your retina. And this is the case for instance, the all vision perception, where it's an ill-posed problem. Given one image on your retina, you have 1,000 or unlimited interpretation of this image. But you have to choose one interpretation. And you choose this interpretation usually using priors. So here, for instance, I may have the prior that it's more probable that I am looking to a cube than to a more complicated shape. So if I'm looking to a cube, there is only two interpretations that are in concurrency, no more than two, okay? And I have to choose, and hard time to choose between these two, but I have only to choose between two. So the priors are the knowledge you have about the physical world that help you to choose between the possible interpretation. And illusion are usually the case where your priors leads you to make the wrong choice. So that's why a lot of illusion were well interpreted by probability distribution. In fact, let me come back. In fact, just to say a word, well, here if you have a thesis that has been made by Jean Laurence about illusion due to the vestibular system for astronauts. Here you have work about some sorry, by Francis Collard about illusion, visual illusion, and so on. This is only to cite some work that has been made in our groups using probabilistic programming. But in fact, in the psychophysics literature, you have hundreds of works that have been made using Bayesian modeling. I will just go in some more details about work made by Estelle Gillet in his PhD thesis about scripting. So scripting has very interesting features. For instance, one feature is motor equivalence. So you learn how to write with your right hand, if you are right-handed, or your left hand. But in fact, you are able to write with any part of your body. For instance, with your fingers, your toes, but also with your nose, also with your regard, also with your hand holding a stick of any kind of length of stick. Well, you are able to write with any part of your body, and this is what is called motor equivalence, because you learn to write with a very specific part, and you are able to transpose that to any other part of your body. And this is a very mysterious process, in fact. For instance, here you have, so that's the script with the right hand, and then you have the left hand, and you have different other part of the body. And you see that it's possible to write with this different part, but even more astonishing, you are able to recognize the kind of scripting because the letters are written with the same style, okay? Another very interesting feature is that there may be very well action simulation during perception. So, for instance, if you look at a movie of dancers, if you are a dancer, we can observe some activity in your brain, in the motor part of your brain. For me, if you observe my brain looking at dancers, there will be absolutely no activity. But if I observe skiers, for instance, there will be clearly an activity in my motor part of the brain. So for scripting and writing, it's the same thing. Here you have fMRI images of someone writing, and you see activity in the motor part of the brain. And here, sorry. Here you have the image when writing pseudo letters, and you observe no activity in the motor part. And here you have the fMRI images of someone looking at real letters that he can write. He knows how to write, and you observe activity in his motor part of the brain. So this is really interesting. It says that to perceive, if we are perceiving something that we are able to do from a motor way, then there is some activity in the motor part of our brain. And we use this activity to help the perception, especially when it's difficult. We did a lot of work about speech, and in speech is the very important part. There are two opposing theory in perception of speech, because perception of speech is a very difficult task, because you are able to recognize the same word, the same speech coming from very different persons. For instance, a small child, a woman, and an adult woman, and an adult male. The sounds are very different, and you recognize the same words and the same sentences. So the real question is, where is the invariant? Because you need to have some point and invariant to be able to recognize what words are pronounced. And this is really a question that has been a very important question for the last 50 years of speech recognition. What is the invariant? And clearly, it's difficult to think that the invariant is only in the sounds. So a concurrent theory is to say that the invariant may be in the motor part. So when you hear a sound, you imagine your motor command to produce the same sound. Okay? You hear an A or an O pronounced by a baby, you imagine the motor command you should send to your larynx and your tongue to pronounce the same O and the same A's and the baby. And this would be the invariant that you could recognize as an A or an O. Well, I simplified a lot, but this is the basic idea. So that...
Excuse me?
Yes?
Do you know if this activity has any link with mirror neurons?
That's a good question. I'm not sure I can make a categorical answer to that. Well, it's quite a complicated subject. I would answer that clearly the answer can be a direct relation with mirror neurons. You have really to go in some details to try to imagine how this can be implemented in brain. And well, I can give you a pointer to one paper on this subject at the end, if you want.
Okay.
Where there is some explanation of how this kind of I would say action perception theory could be implemented in the brain. But
Okay.
it's a really complicated matter.
Okay. Thank you.
So to come back to writing, Estelle Gillet propose the Bayesian action perception model. So it's a probabilistic model with hundreds of variables. And well, you have here and here the probabilistic part that linked the letters and the scriptors to the perception of letter at different level. You have here the pure perception level. You have here the motor that's able to control writing, and you have here finally a model of how to simulate writing in order to help the recognition of the letter. So you have the color to identify the different parts, but you have to know that each of these variables is in fact a combination of several variables itself. So the total is something like 200 or 300 variables in the whole model. So we can ask to this model to do different tasks. The first one is to do letter recognition. So this is the question where you look for the probability distribution on the letters, knowing the perception and knowing the scripter. So this is the computation you have to do. It looks complicated. In fact, it's not very complicated. It's just a product of different probability distribution, and it can easily be made on a computer. And this is the recognition. The goal of, well, the results are not at the standard of the letter recognition of industrial software, not at all, but this is not the goal. We can ask also scripter recognition. So according to a given letter, and knowing this letter, we can ask who is writing this letter, and we see different results where we have very good results for Jean-Louis, who is a very precise and good writer. Estelle and Julienne are quite okay, but clearly Christophe is a very bad writer and very difficult to recognize because he is not very stable in the way he writes. We can do motor control. So we can ask what should be the command that could be sent to a robot knowing the letter and the scripter. And here it's very interesting because we can reproduce the style of a scripter after some learning. So here are A that the robot writes with the style of Estelle, and here A that the robot writes with the style of Christophe. And you can see that it's quite different. There is also, for a given scripter, some variability that can be reproduced by the robot. This is due to the probabilistic representation. When you decide of the motor command, you don't always decide of the same command, but there is a variability. What's interesting is that you can have really a reproduction of motor equivalence. In fact, Estelle, during his PhD, was also the president of the association to participate in the robotic challenge. So they built this robot, which is an holonomic robot with 3 wheels. and that can go in any kind of direction using these three wheels. So this is a robot very different from an arm, and she also built small arms with 2 degrees of freedom. And finally, she used a simulator of a 2 degree of freedom arm. So that's in some sense 3 different kind of robots. And after the learning, you can try to command these 3 robots. So here the command is acceleration on angles. Here it's speed on the 2 angles. And here it's rotation speed for the 3 wheels. And we observe the motor equivalence. So this is the simulated arms. This is the robotic arms. This is the holonomic robot. And for instance, writing a W with the S-tail side, writing an N, sorry, with the S-tail side, gives these 3 results. And you see that there is a similarity, a high similarity between the 3 robots, even as they use very different effectors. And if you change the style of the writer, Christophe, you obtain also similarity, but with a different style of writing. You can ask to the model to do copying of letters. And there is 2 different kind of copy. There is a copy where you don't recognize the letter before writing it. So there is a shortcut here. I have no time to explain the mathematical way to do this shortcut, but there is a shortcut, and what the robot is reproducing is the shape of what it observes. So here for a kind of alpha, the robot is reproducing an alpha. Here for a kind of W, it's reproducing a kind of W. But then you can also ask the copy using the recognition of letter. So you perceive a shape, you recognize the letter, and then you rewrite this letter. And in that case of copying, you obtain very different result, because when you show the robot an alpha, alpha is not a letter that was learned by the robot. So the robot recognizes an N. I don't know why, but it recognizes an N. And it rewrites an N, which of course is completely different of the alpha. And for the W, it recognizes a W, but rewrites the W in a different style. Okay, now we can make the robot in more difficult reading task, where it's not very obvious to recognize the letter. And then with using this model, it can do action simulation to try to recognize the letter. So here is the letter. I don't know what letter you recognize here, but in fact, the robot is recognizing a G, because it makes some simulation. And to go from this point to this point, you need to have a trajectory of this kind. And then when you complete this trajectory, okay, like here, then it's clear that it's a G. I don't know if you recognize a G when you saw that, but in fact, this is a kind of task that humans are very performant to do, to recognize letter from partial information. Okay, well, I show you this next recess, but I am very late. But this one, I love it, so.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
But how did you know?
Madam, as any horticulturist will tell you, one does not plant petunias until May is out. Take her away.
Sorry, madam.
It's just a matter of observation. The real question is, how observant were you?
Action.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
Oops. Okay. So I think it's very interesting because did you notice even a single one of the 21 changes? Here again is an impressive example of the way that you should not be at all confident in your perception, and your perception are completely oriented toward a specific goal. What's interesting here, I don't know if you notice at the end of the movie, it is not a scientific experience. It's an advertisement from the public London transportation to say that you should be careful about cyclists when you are driving on the road, because your attention may be disturbed by a lot of different aspects. But anyway, I think it's a really impressive demonstration that your perception is always completely oriented. Okay, I am very late. I will just maybe try to give you some very quick hints about how can Livex system do inference, probabilistic inference. And in fact, there are different levels in this question. We already saw that at the macroscopic level, probabilistic inference can be very interesting to explain a lot of psychophysic experiences. Here the question is a little bit different, is at microscopic and mesoscopic level, is it possible to say that neurons, the nervous systems, or even, as you will see, a more microscopic part, can do probabilistic inference? So at the level of neurons and assembly of neurons, there is a real community working on that, with a very eminent specialist of that in Paris, for instance, and in France. with Sophie Denève at École Normale Supérieure, Alexandre Prouget, which is in Switzerland, but okay. So I will not present this work because it's suppose a course of 3 hours by itself. But here are some pointers to start on this subject, which is very interesting. I will just maybe try to give you some hints about how can very simple, much more simple organism can do or may do something looking like probabilistic inference. And for instance, here Chlamydomonas is back. So it is this algae, single cell algae, and it has a very interesting feature. Of course, it has no nervous system, which because it's a single cell being, but it has a small flagella, I guess, and it is able to swing in a given direction, and it has also a very impressive small part, which is the equivalent of an eye. It is able to measure the intensity of light coming in a given direction, and as having only one direction is not sufficient, it swims in a spiral way, turning around its axis. So this small eye spot is scanning like a radar to obtain a much more precise direction of the light. What we study is that cell signaling could be a possible support of some inference, because this algae is able to do inference. In fact, it is able to swim toward the right part of the environment with the right illumination to get energy from the light. But it is also able to swim away from a part of the environment where there is too much light, and too much light could cause damage to the algae. And these algae are very performant to solve this kind of problem. In fact, a very strange and interesting job was done in collaboration between the museum and an artist. And by illuminating the algae with the projection of a photography, the quantity of algae at a given point reproduce the gray level of the photography. So you obtain the image made by the concentration of algae in their environment, which is very impressive on their ability and their sensibility to the way they move toward light. So what is cell signaling? Inside a given cell, there is a constant interaction between macromolecules, which can macromolecule and much smaller molecules that are called messengers. and macromolecules can change states according to their interaction with messengers. So here you have a schematic representation of this, where you have here a macromolecule with 8 different states, and it can switch from one state to another state according to the fact that it interacts with a given messenger. So here, for instance, the green triangle is fixed by the macromolecule. We switch to the state where this green messenger is fixed, and so on. And you have 8 states. And some of these states can be active, here represented by the yellow star. And when these states are active, the macromolecule usually is able to produce or to release some new messenger in the environment that can go to interact with other macromolecules. An example of these macromolecules are ionic canals. And each of our cells, we have hundreds or thousands or even more of these ionic channels that are able to open and close. This is the view of an ionic canals. This is the skin of the cell, and this here, the ionic channel is opens, and some ions goes from outside of the cell to inside of the cell. It can be closed also. Here is a picture, a schemata of ionic channels at the atomic level. So each small point here is an atom. And you see that it's like a diaphragm. It can be closed or it can be open. So what's interesting is the scale of this process. So if you take the small sphere of the algae to be the sphere and to around the Eiffel Tower, ion channel will be the size of 1 cent coin. Okay. Macromolecule will be the size of 3 centimeters ball, and a messenger will be the size of a grain of sand. That's to demonstrate that in a single cell like this algae, there is really a lot of room for a lot of interaction and a lot of complexity. This is, I say 3-5 more minutes, and then I will stop, even if it's not completely finished. This is the schemata of cell signaling, a very simplified schemata of only of the part of cell signaling taking place in CLAMI for energy production. Each step here is interaction between messenger and a given macromolecule, releasing some messenger which go to interact with another macromolecule, well, another population of macromolecule, releasing some messenger with interaction to another kind of macromolecule, and so on. Okay, you can see the complexity of this process, even if it's very simplified. And you have hundreds of such processes that occur at the same time in the algae to regulate all its behavior and so on. What can be demonstrated is that this cellular mechanism, cell signaling mechanism, and a given probabilistic model can both be mathematically represented by RFNC, which is a rational function with non-negative coefficient. So there is a possible equivalence between the two. Of course, we don't know for a given probabilistic model what could be the cell signaling process that implements this computation. And the other way around, we don't know for a given cell signaling process what could be the probabilistic problem that it is solving. But here, at least, we have a mathematical kernel that is common to the two processes. Okay, I will stop here. I'm out of time. Well, here are the two books that are at your disposition. There are a lot of other pointers that I give you, either to papers, to theses, and to also I concentrate on the work that were made in our groups in Grenoble, Paris, and Switzerland, and so on. But I can, if you are interested, also give you pointers to works of a lot of people. Especially, I should put a reference to a book on robotic programming, which is very interesting, written by a German guy who is working at Stanford. Well, if you have any question.
Yeah, just about the references, you also mentioned that you could give references about the simulation of action when it was perceived, and how it could be implemented in the brain, and yeah, about mirror neurons too, as Josephine said. If you could give some references about this.
Yes. I have to find it. Do you have a mailing list? Or something?
Yeah, okay.
Maybe it's better that I send to the mailing list the reference, because I have to search for it.
Yeah. It's perfect with the mailing links. Or I don't know if you have access to Schoology.
Yes, I think so.
Because we have a module for this course, and yeah.
Okay.
Send to Mehdi, and Mehdi can put on Schoology.
I will try using
maybe.
Schoology. If I don't succeed, I will go. I will go through Mehdi to do it. Okay.
All right. Thanks a lot.
Thank you. I had just one more question. I'm not sure if it's very well formulated, but we have this apparent dichotomy between the fact that Bayesian inference is seemingly...
Sorry, I have very hard time to hear you.
Okay, I speak loud. We have this dichotomy between the fact that Bayesian inference is apparently performed by neural circuits in the brain, in theory, versus the fact that consciously we cannot perform very easily calculations with probabilities. And I just wondered what have been some people's ideas as to why we have this conflict, or what are some explanations?
Well, if I understand well your question, I think it's a very different process to have unconscious processing for perception and motor control using probability, and being able to do conscious probabilistic calculation. Okay?
Yeah.
It's a little bit the same with logic, in fact. For a long time, logic has been the model of rationality in the brain. But even so, a lot of people are not able to do formal, logical, mathematical reasoning. Even if they are, I'm not saying that they are not rational. I'm saying that they are not able to formalize and to communicate with others under a mathematical way, a logical reasoning. I think it's about the same for probability. It's not because your nervous system and your body is able to do probabilistic reasoning that you are able to formalize a probabilistic calculation and to communicate under mathematical form to someone else. Okay, it's two completely different processes. Another point maybe that is important to say is that there is no proof that at nervous system or there is some probability reasoning going on. I mean, this is a point of view, an hypothesis that is interesting to interpret some observation and data. But there is no proof that it's what's really going on.
Yeah, makes sense. Thank you.
I'm trying to stop the